called a difference quotient. F of x minus f of a over x minus a. There's the definition of derivative. Okay. Where again, this part here, we'll just write a word. It's the limit of a difference quotient. Limit of a difference quotient. I haven't used that terminology. Difference quotient. Difference quotient. Okay. Everybody okay so far? What we're trying to do? We want to find slopes and curves. How do you do that? You take secant slopes closer and closer to the tangent line slope. And since we're using a limit, this will be exact. Yeah.
Since the limit is not going to reach there.
You will never reach there, but it tells you what it's heading towards. Remember what limits tell you. So even though it's never going to actually become the tangent line slope, the computation we'll make with this limit will tell you what that is supposed to become. Even though x will never reach a, right? But it always tells you what you're heading towards. So it's going to tell you exactly what that purple line slope is, because that's where you're heading. You're heading towards the purple line slope. So out of this computation here will come purple line slope, even though x never reaches a. It's telling you what it's heading towards. It's heading towards that slope. Right? Just like when there's a hole, even though you don't get to that hole, it tells you the whole value, right? All right. There's a different way to write this, and it is the one that you will use more often. Okay? There's a small change of variables you can make to this definition, and that is let x minus a equal h. If x minus a equals h, then it can be written like this. Limit of x must be a plus h. Agreed? If x minus a is h, then x is a plus h, right? Okay. So limit of f, a plus h, minus f of a, over, but x minus a is h itself. We have this formula instead. What's h heading towards? If x is heading towards a, what is h heading towards? Right, 0. Right? If x is heading towards a, this quantity here, x minus a, is heading towards 0. So therefore h is heading towards 0, and there's our new limit defined in terms of h, a shrinking h. So there's version 2, which is, I would say, the more widely used one. The symbol that we use to represent this, without all the definition, but just the symbols, would be f prime at a. The derivative of f at this location, right? That's what f prime means. Derivative of f, meaning the slope of f, the slope of the curve, at said location, all right? That's notation used. That's what it means. Derivative of f at a. Any questions so far?
What does that word say for
Limit. Get a little messy here. No, you guys good? Conceptually, that's the concept of trying to do. Now we'll say how it shows out. How it shows out in practice. Well, tell me about. What chapter?
3.1.
3.1. All right, let's do a few problems. So, again, in this first section, we are using a limit definition, which you will not have to use too much after 3.1. We'll have very special rules we will use to compute derivatives. We won't have to resort to the definition much longer. Okay. Number 17. Find the slope of the tangent line of f at the point P. Okay. I hate to erase this picture, it's so good. Whatever. All right. (17) and 3.1. Find slope of tangent line to f of x equals 2x plus 1. So we have a linear function. It should be pretty easy. at the point 0, 1. We should know the answer already just by thinking. What's the slope of the line? That's the answer, right? Since the slope is never changing, it's a constant slope, it's a slope everywhere. I don't care where you go. I don't care if you go to 0, 1, you go to 1, 3, wherever you go on that curve, the slope is going to be 2. So we expect our answer to be 2. Remember, the derivative is the slope of the curve. So for constant slope functions, which are lines, it's always that number there at the end. Let's compute it using the definition like they said. That's what we're really supposed to do. All right, so I need to compute the limit as h approaches 0 of f of a. So what's a? Okay, I'll write the letter first. Hold on a second. I'll just write it in abstract here. Okay, so for now, for our problem, what is the letter a? What number is it? Remember that a is what x is approaching. 0. It's approaching 0. It is approaching the x value for this point. Okay? And what's the function? 2x plus 1. So I need to replace these symbols now. Limit as h approaches 0. So this will be replaced with 2x plus 1, the function. But I'm going to put a plus h, which is 0 plus h for us, in place of x. So we'll read 2, 0 plus h plus 1. That's this part alone. Everybody see that? It's okay? Make sense? Our function is that. So 2, right? That was x. 2x plus 1 is our function. I need to put in that function a plus h. Our a is 0, so 0 plus h goes in for f. Minus f of a. Minus f of 0. So 2, 0 plus 1. Right? The value of the function at 0. Which we already know is going to be 1. We gave us that value right there, right? 0, 1. All right. Divided by h. Now, what you should notice is something that came up in a lot of the limit problems we did in chapter 2, and that is, if you think about the top, what is the top heading towards? It's certainly heading towards 0, right? As h goes towards 0, this gets closer and closer to f of a, but f of a minus something really close to f of a minus f of a is heading towards 0. At the bottom, it says it's heading towards 0. So this is a 0 of 0 case, right? Every derivative you ever take is always a 0 of 0 case. So there's hope. And we expect that we should be able to find a factor of h up here to cancel with this one, and be able to evaluate it directly by plug and chug. Remember those problems? You got their peaches? Cantaloupe? Apricot. Okay. 2h plus 1. Limit. As h approaches 0, we expect to find a factor of h above. A factor of h, what we expect? 2h plus 1 minus 1 over h. 1 minus 1 is 0. We have 2h over h. 2h over h. There is our hidden factor of h. h over h is 1. So we get the limit of 2 as h approaches 0. What is the answer? 2. Right? The limit of a constant is that number. Right? Everybody agree? Limit of a constant?